In this lesson, we're looking at solving exponential equations using logarithms. And really, the only other way we've looked at so far for solving an exponential function is by getting a common base on each side and then setting the exponents equal to one another. All right. What we're going to do today is basically look at examples where we can't do that. All right. When I can't get a common base and set the exponents equal to each other, that's when logarithms come into play. And once again, these are our three inverse properties of logarithms. The one that we're going to be really focusing on and using today is this one in the middle. Okay. To solve logarithmic equations, we used this last one because here the exponential function is undoing the logarithm. Well, now today we're using this one because here the logarithm is undoing the exponential function. That's what we're looking at today. We're going to take exponential functions and solve them using logarithms. Okay. So when we do this, the first thing we do is we isolate the exponential part of the function. So whatever's being raised to a power, we got to get that thing by itself. All right. We move everything else to the other side of the equation. We get the thing being raised to a power all by its lonesome. All right. Then we're going to take the logarithm of each side. We're going to use that middle property to undo the exponential functions. We're going to use a logarithm to get rid of the exponential function. And then we're just going to solve what's left. Once the exponential function has been eliminated, we're going to see what we have left, plug it into our calculator, and go from there. Okay? For example, if I look at this one, I've got 5 to the a equals 120. Again, I can't write these as a common base. There is 5 to no power that I can think of will give me a 120. 5 to the second is 25. 5 to the third is 125. So it's kind of in between there. It doesn't work with that first method. So this is why we use logarithms. So the first thing I do is isolate the exponential part of the function, which it's already isolated. The thing being raised to a power is already by itself. So now I have to undo 5 raised to a power. Right now I have 5 raised to a power. I want to undo that. And if I want to undo 5 raised to a power using a logarithm, I have to use log base 5. See, remember the bases here have to be the same. That's what this rule up here is saying. It's saying, hey, when the base of the logarithm and the base of the exponential function are the same, they cancel out, and I'm just left with the exponent. So here the base of the exponential function is 5, so I need to use log base 5 in order to get rid of this thing. All right? Whatever I do to one side, I also have to do to the other side, so I have to do log base 5 to the other side as well. So now what happens is log base 5 and the 5 cancel out, so I'm just left with an a. Over here I have log base 5 of 120, and that is really a job for my calculator. Remember, when I want to plug this thing into the calculator, I just do the natural log of 120 divided by the natural log of 5 using my change of base formula. Okay, so I go ahead and plug that in, and that gives me approximately 2.975 when it's rounded off. Okay, and so this is my answer, and it should make sense because when you think about it, 5 to the second power is 25, 5 to the third power is 125, so I'm somewhere in between there, but I'm obviously closer to the 125 than I am to 25, which means that the a value has to be closer to 3 than it is to 2, so 2.975 makes sense. And if you plug this back in, it's not going to give you exactly 120 because I rounded this answer off, but it's going to be very, very close. Okay? If I take a look at the next one, again, if I want to undo 6 raised to a power, I'm going to do log base 6 of each side. So let me rewrite this to give myself a little bit of space in front of that 45.6. To undo 6 raised to a power, I do log base 6 of each side. And what happens is log base 6 and the 6 cancel each other out, so it leaves me with just an x. Over here, again, this is a job for my calculator. I'm going to plug this in using my change of base formula. I'm going to do the natural log of 45.6 divided by the natural log of 6. Okay, so now I plug this into my calculator, and it looks like it gives me approximately a 2.132 when it's all said and done. And you can plug that back in to check and see if it works. All right. Now, the interesting part about this is when I do these, I tend to choose a base that's going to cancel nicely, but I could have used any logarithm I want. Let me just show you that real quickly. I could have used the natural log for each of these. So like this first one, if I had 5 raised to the a equals 120, I could just take the natural log of each side, and now I just have to use properties of logarithms. Remember, properties of logarithms allow me to bring this a value out front and make it multiplication when I expand. So it becomes this. And so now when you think about it, I have a times the natural log of 5 to undo multiplication. I divide, so I divide each side by the natural log of 5. And you see what I'm left with is a equals the natural log of 120 divided by the natural log of 5. Well, that's what I did when I did my change of base formula. This is why the change of base formula works. Because properties of logarithms allow us to bring that exponent down in front of any logarithm, that's why we can change any logarithm to whatever we want and plug it into our calculator through division. Okay, and so it gives me the same thing. And I could do the same thing with the next one as well. I could plug this in and use my natural log, and you can see kind of how the change of base formula works when we do that. If I take the natural log of each side, I bring the x out front, and now I'm going to divide by that natural log of 6. Okay, so this is why the change of base formula actually works, is because it's the same process as solving using any logarithm. Okay, and so you can see I'm going to get the same thing there. But for the most part, with these really simple examples, it's probably easier just to use the base that I have written here. Okay. If I look at the next one, again, the exponential function's not by itself this time, so I have to get it by itself, so I'm going to add 2 to each side. When I do that, I end up with 5 raised to the w plus 3 equals 19. Now to undo 5 raised to a power, I do log base 5. Again, you could just use the natural log here and then go from there. When it's a simple example like this, you might as well just do the base that matches. So now here, log base 5 and the 5 cancel. Leaves me with a w plus 3. Over here I have log base 5 of 19. And now I'm going to subtract the 3 from each side. And really this just becomes a job for my calculator. When you plug this in, make sure you do the natural log of 19 divided by the natural log of 5, and then hit enter, and then subtract the 3, just because it makes things work out just a little bit better. When you do that, you should get a negative 1.171 when it's all rounded and settled down. Okay. If I look at the next one, again, the exponential part is not by itself, so I got to get it by itself. I'm going to divide each side by the 3. So now I get the exponential part by itself. This equals 9. To undo to undo 4, I have to do log base 4. Whatever I do to one side, I have to do to the other side. Okay, and so now again, over here these cancel, leaves me with a 2x. Over here I have log base 4 of 9, and now I have to divide each side by 2. Again, when you plug this into your calculator, kind of take charge of order of operations yourself. Do the natural log of 9 divided by the natural log of 4, hit the enter button, which gives you a 1.585, then divide that by the 2, and hit enter again, and you'll get a 0.792. Okay, because we want to have a lot of accuracy on these, because exponential functions, as soon as we lose that little bit of accuracy, they can become drastically different in the long term, okay, as we start increasing these things. If I look at this one, again, I got to get the exponential part by itself, so I'm going to subtract the 10 from each side. So I end up with 2 to the x minus 4 equals, that's going to give me a 72. And now to undo 2 raised to a power, I have to do log base 2. Whatever I do to one side, I have to do the other side. Over here, the log base 2 and the 2 cancel, leaves me with an x minus 4. And now I add the 4 to each side. Again, just be careful plugging these into the calculator. Kind of take charge of order of operations yourself. Do the natural log of 72 divided by the natural log of 2. Hit the enter button, and then add the 4 and hit enter again. Okay, so kind of do it in 2 steps there. Don't round anything off as you're plugging it into your calculator, but do it in 2 steps, and to 3 decimal places this rounds to 10.170. Okay. If I look at the next one, the exponential part here is by itself, so I'm going to do log base 30 of each side this time. Let me give myself a little space. So to undo 30 raised to a power, I don't know what I just wrote there. Let me try that again. Oh boy. To undo 30 raised to a power, I have to do log base 30 of each side. Whatever I do to one side, I have to do to the other side. Over here, the log base 30 and the 30 cancel, leaves me with an x squared. Over here, really, this is a job for my calculator, but then I'm also going to take the square root. And again, just be really careful plugging this into the calculator. Me personally, what I like to do is I like to punch in the natural log of 50 divided by the natural log of 30. And that gives me a decimal, and then I'm going to do the square root of the answer. There's a little button that says ANS on your calculator. If you do the square root of an answer, it gives you 1.072 when it's all said and done. Okay, technically it would be plus or minus that, so I should probably put that here. Almost forgot that plus or minus because I took the square root of each side. And we tend to throw out the negative answers here because we're used to solving logarithms, but that's not the case in this one because it's an exponent. Negative answers are fine. Okay.